What is up, party people? It's Keys Dan with RadioWhat.com, DJLittleRock.com, coming to you live and in living color from the Radio What studio. And this is my podcast, What Makes You Famous. It's an extension of the RadioWhat.com internet radio station that I've been running for quite some time. And if you need DJ services, where do you go? DJLittleRock.com. Check availability and get a free price quote. And maybe you could have me. Oh yeah, I like to play for the people at your next events. You know, I like weddings and parties of all kinds. Video dance party karaoke jams have been what's going on lately. If you'd like to tell your story, I encourage you to check out my other podcast, What Makes You Famous. Find it everywhere using the hashtag What Makes You Famous. Now, on with the show. Today on the program, the solar system. Yes, the solar system is one of my favorite systems in this galaxy. Why? Well, maybe I'm biased. I live here. And so do you, probably. Who knows where this podcast is going to go? The solar system is the gravitationally bound system of the sun and the objects that orbit it, either directly or indirectly. Of the objects that orbit the sun directly, the largest are the 8 planets, with the remainder being smaller objects, the dwarf planets, and small solar system bodies. Of the objects that orbit the sun directly, the moons, 2, are larger than the smallest planet, Mercury. The solar system formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority of the system's mass is the sun, with the majority of the remaining mass contained in Jupiter. The 4 smaller inner planets, Mercury, Venus, Earth, and Mars, are terrestrial planets, being primarily composed of rock and metal. The 4 outer planets are giant planets, being substantially more massive than the terrestrials. The 2 largest, Jupiter and Saturn, are gas giants, being composed mainly of hydrogen and helium. The 2 outermost planets, Uranus and Neptune, are ice giants, being composed mostly of substances with relatively high melting points, compared with hydrogen and helium, called volatiles, such as water, ammonia, and methane. All 8 planets have almost circular orbits that lie within a nearly flat disk called the ecliptic. The solar system also contains smaller objects, the asteroid belt, which lies between the orbits of Mars and Jupiter, mostly contains objects composed, like terrestrial planets, of rock and metal. Beyond Neptune's orbit lie the Kuiper belt and scattered disks, which are populations of trans-Neptunian objects composed mostly of ices, and beyond them, a newly discovered population of sednoids. Within these populations, some objects are large enough to have rounded under their own gravity, though there is considerable debate as to how many there will prove to be. Such objects are categorized as dwarf planets. Identified or accepted dwarf planets include the asteroids Ceres and the trans-Neptune objects Pluto and Eris. In addition to these 2 regions, various other small body populations, including comets, centaurs, and interplanetary dust clouds, freely travel between regions. 6 of the planets, the 6 largest possible dwarf planets, and many of the smaller bodies are orbited by natural satellites, usually termed moons, after the moon. Each of the outer planets is encircled by planetary rings of dust and other small objects. The solar wind, a stream of charged particles flowing outwards from the sun, creates a bubble-like region in the interstellar medium, known as the heliosphere. The heliopause is the point at which pressure from the solar wind is equal to the opposing pressure of the interstellar medium. It extends out to the edge of the scattered disk. The Oort cloud which is thought to be the source for long period comets, may also exist at a distance roughly 1,000 times further than the heliosphere. The solar system is located in the Orion Arm, 26,000 light years from the center of the Milky Way galaxy. That's an overview of the solar system. Now let's get into discovery and exploration. For most of history, humanity did not recognize or understand the concept of the solar system. Most people, up to the late Middle Ages, Renaissance, believed Earth to be stationary at the center of the universe and categorically different from the divine ethereal objects that move through the sky. Although the Greek philosopher Aristarchus of Samos had speculated on heliocentric reordering of the cosmos, Nicholas Copernicus was the first to develop a mathematically predictive heliocentric system. In the 17th century, Galileo discovered that the sun was marked with sunspots and that Jupiter had 4 satellites in orbit around it. Christian Huygens followed on from Galileo's discoveries by discovering Saturn's moon, Titan, and the shape of the rings of Saturn. Edmund Halley realized in 1705 that repeated sightings of a comet were recording the same object, returning regularly once every 75 to 76 years. This was the first evidence that anything other than the planets orbited the sun. Around this time, 1704, the term solar system first appeared in English. In 1838, Frederick Bessel successfully measured a stellar parallax, an apparent shift in the position of a star created by Earth's motion around the sun, providing the first direct experimental proof of heliocentrism. Improvements in observational astronomy and the use of unmanned spacecraft have since enabled the detailed investigation of other bodies orbiting the sun. Now, to structure and composition. The principal component of the solar system is the sun, a G2 main sequence star that contains 99.86 of the system's known mass and dominates it gravitationally. The sun's 4 largest orbiting bodies, the giant planets, account for 99% of the remaining mass, with Jupiter and Saturn together comprising more than 90%. The remaining objects of the solar system, including the 4 terrestrial planets, the dwarf planets, moons, asteroids, and comets, together less than 0.002% of the solar system's total mass. Most large objects in orbit around the sun lie near the plane of Earth's orbit, known as ecliptic. The planets are very close to the ecliptic, whereas comets and Kuiper belt objects are frequently at significantly greater angles to it. As a result of the formation of the solar system, planets and most other objects orbit the sun in the same direction that the sun is rotating, counterclockwise, as viewed from above Earth's North Pole. There are exceptions, such as Halley's Comet. Also, most of the larger moons orbit their planets in this prograde direction, and most larger objects rotate themselves in the same direction, being a notable retrograde exception. The overall structure of the charted regions of the solar system consists of the sun, 4 relative inner planets surrounded by a belt of mostly rocky asteroids, and 4 giant planets surrounded by the Kuiper belt of mostly icy objects. Astronomers sometimes informally divide this structure into separate regions. The inner solar system includes the 4 terrestrial planets and the asteroid belt. The outer solar system is beyond the asteroids, including the 4 giant planets. Since the discovery of the Kuiper belt, the outermost parts of the solar system are concentric region consisting of the objects beyond Neptune. Most of the planets in the solar system have secondary systems of their own, being orbited by planetary objects called natural satellites or moons, two of which, Titan and Ganymede, are larger than the planet Mercury. And in the case of the four giant planets, by planetary rings, thin bands of tiny particles that orbit them in unison. Most of the largest natural satellites are in synchronous rotation, with one face permanently turned toward their parent. Kepler's laws of planetary motion describe the orbits of objects about the sun. Following Kepler's laws, each object travels along an ellipse with the sun at one focus. Objects closer to the sun, with smaller semi-major axes, travel more quickly because they are more affected by the sun's gravity. On an elliptical orbit, a body's distance from the sun varies over the course of its year. A body's closest approach to the sun is called perihelion, whereas the point from the sun is called aphelion. The orbits of the planets are nearly circular, but many comets, asteroids, and Kuiper Belt objects follow highly elliptical orbits. The positions of the bodies in the solar system can be predicted using numerical models. Although the sun dominates the system by mass, it accounts for only about 2% of the angular momentum. The planets, dominated by Jupiter, account for most of the rest of the angular momentum due to the combination of their mass, orbit, and distance from the sun, with a possibly significant contribution from the comets. The sun, which comprises nearly all the matter in the solar system, is composed of roughly 98% hydrogen and helium. Jupiter and Saturn, which comprise nearly all the remaining matter, are also primarily composed of hydrogen and helium. A composition gradient exists in the solar system, created by heat and light pressure from the sun. Those objects closer to the sun, which are more affected by heat and light pressure, are composed of elements with high melting points. Objects farther from the sun are composed largely of materials with lower melting points. The boundary in the solar system beyond which those volatile substances could condense is known as the frost line, and it lies roughly at 5 AU from the sun. The objects of the inner solar system are composed of mostly rock, the collective name for compounds with high melting points, such as silicates, iron, or nickel, that remain solid under almost all conditions in the protoplanetary nebula. Jupiter and Saturn are composed mainly of gases, the astronomical term for materials with extremely low melting points and high vapor pressure, such as hydrogen, helium, and neon, which were always in the gaseous phase in the nebula. Ices like water, methane, ammonia, hydrogen sulfide, and carbon dioxide have melting points up to a few hundred kelvins. They can be found as ices, liquids, or gases in various places in the solar system, whereas the nebula, they were either in the solid or gaseous phase. Icy substances comprise the majority of the satellites of the giant planets, as well as most of Uranus and Neptune, the so-called ice giants, and the numerous small objects that lie beyond Neptune's orbit. Together, gases and ices are referred to as volatiles. Still with me? Let's get into distances and scales. The distance from the Earth to the Sun is 1 astronomical unit, or AU, 150 million kilometers, or 93 million miles. For comparison, the radius of the Sun is 0.0047 AU, or 700,000 kilometers. Thus, the Sun occupies 0.00001% of the volume of a sphere with a radius the size of Earth's orbit, whereas Earth's volume is roughly 1/1,000,000th that of the Sun. Jupiter, the largest planet, is 5.2 astronomical units, or 780 million kilometers from the sun, and has a radius of 71,000 kilometers, or 0.00047 AU, whereas the most distant planet, Neptune, is 30 AU from the sun. With a few exceptions, the farther a planet or belt is from the sun, the larger the distance between its orbit and the orbit of the next nearer object to the sun. For example, Venus is approximately 0.33 AU farther out from the sun than Mercury, whereas Saturn is 4.3 AU out from Jupiter, and Neptune lies 10.5 AU out from Uranus. Attempts have been made to determine a relationship between these orbital distances. For example, the Titus-Bode law. The Titus-Bode law is a hypothesis that bodies in some orbital systems, including the sun's, orbit at semi-major axes in a function of planetary sequence. The formula suggests that extending outward, each planet would be approximately twice as far from the sun as the one before. But no such theory has been accepted. Some solar system models attempt to convey the relative scales involved in the solar system on human terms. Some are small in scale and may be mechanical, called orreries, whereas others extend across cities or regional areas. The largest such scale model, the Sweden solar system, uses the 110 meter or 361 foot Ericsson globe in Stockholm as its substitute sun. And following the scale, Jupiter is a 7.5 meter sphere at Stockholm Arlanda Airport, 40 kilometers away, whereas the farthest current object, Sedna, is a 10 centimeter sphere in Luleå, 912 kilometers away. If the Sun-Neptune distance is scaled to 100 meters, then the Sun would be about 3 centimeters in diameter, roughly 2/3 the diameter of a golf ball. The giant planets would be smaller than about 3 millimeters, and Earth, along with that of the other terrestrial planets, will be smaller than a flea, 0.3 at this scale. Are we having fun or what? Now let's go through the formation and evolution of the solar system. The solar system formed 4.568 billion years ago from the gravitational collapse of a region within a large molecular cloud. This initial cloud was likely several light years across and probably birthed several stars. As is typical of molecular clouds, this one consisted mostly of hydrogen, with some helium and small amounts of heavier elements fused by previous generations of stars. As the region that would become the solar system, known as the pre-solar nebula, collapsed, conservation of angular momentum caused it to rotate faster. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. As the contracting nebula rotated faster, it began to flatten into a protoplanetary disk with a diameter of roughly 200 AU and a hot, dense protostar at the center. The planets formed by the accretion from this disk, in which dust and gas gravitationally attracted each other, coalescing to form ever larger bodies. Hundreds of protoplanets may have existed in the early solar system, but they either merged or were destroyed, leaving the planets, dwarf planets, and leftover minor bodies. Due to their higher boiling points, only metals and silicates could exist in solid form in the warm inner solar system, close to the sun. And these would eventually form the rocky planets of Mercury, Venus, Earth, and Mars. Because metallic elements only comprised a very small fraction of the solar nebula, the terrestrial planets could not grow very large. The giant planets, Jupiter, Saturn, Uranus, and Neptune, formed further out, beyond the frost line, the point between the orbits of Mars and Jupiter, where material is cool enough for volatile, icy compounds to remain solid. The ices that formed these planets were more plentiful than the metals and silicates that formed the terrestrial inner planets, allowing them to grow massive enough to capture large atmospheres of hydrogen and helium, the lightest and most abundant elements. Leftover debris that never became planets congregated in regions such as the asteroid belt, Kuiper belt, and Oort cloud. The NICE model is an explanation for the creation of these regions and how the outer planets could have formed in different positions and migrated to their current orbits through various gravitational interactions. Within 50 million years, the pressure and density of hydrogen in the center of the protostar became great enough for it to begin thermonuclear fusion. The temperature, reaction rate, pressure, and density increased until hydrostatic equilibrium was achieved. The thermal pressure equaled the force of gravity. At this point, the sun became a main sequence star. The main sequence phase, from beginning to end, will last about 10 billion years for the sun, compared to around 2 billion years for all other phases of the sun's pre-remnant life combined. Solar wind from the sun created the heliosphere and swept away the remaining gas and dust from the protoplanetary disk into interstellar space, ending the planetary formation process. The sun is growing brighter. Early in its main sequence life, its brightness was 70% that of what it is today. The solar system will remain roughly as we know it until the hydrogen in the core of the sun has been entirely converted to helium, which will occur roughly 5 billion years from now. This will mark the end of the sun's main sequence life. At this time, the core of the sun will contract with hydrogen fusion occurring along a shell surrounding the inert helium, and the energy output will be much greater than at present. The outer layers of the sun will expand to roughly 260 times its current diameter, and the sun will become a red giant. Because of its vastly increased surface area, the surface of the sun will be considerably cooler, 2600 Kelvin at its coolest, than it is on the main sequence. The expanding sun is expected to vaporize Mercury and render Earth uninhabitable. Eventually, the core will be hot enough for helium fusion. The sun will burn helium for a fraction of the time it burned hydrogen to the core. The sun is not massive enough to commence the fusion of heavier elements, and nuclear reactions in the core will dwindle. Its outer layers will move away into space, leaving a white dwarf, an extraordinarily dense object, half the original mass of the sun, but only the size of Earth. The ejected outer layers will form what is known as a planetary nebula, returning some of its material that formed the sun, but now enriched with heavier objects like carbon to the interstellar medium. Let's talk a little bit more about the sun. The sun is the solar system's star, and by far its most massive component. Its large mass, 332,900 Earth masses, which comprises 99.86% of all the mass in the solar system, produces temperatures and densities in its core high enough to sustain nuclear fusion of hydrogen into helium, making it a main sequence star. This releases an enormous amount of energy, mostly radiated into space as electromagnetic radiation, peaking in visible light. The sun is a G2 type main sequence star. Hotter main sequence stars are more luminous. The sun's temperature is intermediate between that of the hottest stars and that of the coolest stars. Stars brighter and hotter than the sun are rare, whereas substantially dimmer and cooler stars, known as red dwarfs, make up 85% of the stars in the Milky Way. The Sun is a population 1 star. It has a higher abundance of elements heavier than hydrogen and helium than the older population 2 stars. Elements heavier than hydrogen and helium were formed in the cores of ancient and exploding stars. So the first generation of stars had to die before the universe can be enriched with these atoms. The oldest stars contain few metals, whereas stars born later have more. This high metallicity is thought to have been crucial to the sun's development of a planetary system because the planets form from the accretion of metals. You've gone this far. Let's keep going. Let's talk about the interplanetary medium. The vast majority of the solar system consists of a near vacuum known as the interplanetary medium. Along with light, the sun radiates a continuous stream of charged particles, a plasma, known as the solar wind. This stream of particles spreads outwards at roughly 1.5 million kilometers per hour, creating a tenuous atmosphere that permeates the interplanetary medium out to at least 100 AU. Activity on the sun's surface, such as solar flares and coronal mass ejections, disturbs the heliosphere, creating space weather and causing geomagnetic storms. The largest structure with the heliosphere is the heliospheric current sheet, a spiral form created by the actions of the sun's rotating magnetic field on the interplanetary medium. Earth's magnetic field stops its atmosphere from being stripped away by the solar wind. Venus and Mars do not have magnetic fields, and as a result, the solar wind is causing their atmospheres to gradually bleed away into space. Coronal mass ejections and similar events blow a magnetic field and huge quantities of material from the surface of the sun. The interaction of this magnetic field and material with Earth's magnetic field funnels charged particles into Earth's upper atmosphere, where its interactions create aurora, seen near the magnetic pole. The heliosphere and planetary magnetic fields, for those planets that have them, partially shield the solar system from the high energy interstellar particles called cosmic rays. The density of cosmic rays in the interstellar medium and the strength of the sun's magnetic field change on very long timescales. So the level of cosmic ray penetration in the solar system varies, though by how much is unknown. The interplanetary medium is home to at least two disk-like regions of cosmic dust. The first, the zodiacal dust cloud, lies in the inner solar system and causes the zodiacal light. It was likely formed by collisions within the asteroid belt, brought on by gravitational interactions with the planets. The second dust cloud extends from about 10 AU to about 40 AU and was probably created by similar collisions within the Kuiper belt. Let's go through the inner solar system. The inner solar system is the region comprising the terrestrial planets and the asteroid belt, comprised mainly of silicates and metals. The objects of the inner solar system are relatively close to the sun. The radius of this entire region is less than the distance between the orbits of Jupiter and Saturn. This region is also within the frost line, which is a little less than 5 AU, about 700 million kilometers from the sun. The inner planets, the four terrestrial or inner planets, have dense rocky compositions, few or no moons, and no ring systems. They are composed largely of refractory minerals such as silicates, which form their crusts and mantles, and metals, such as iron and nickel, which form their cores. Three of the four inner planets, Venus, Earth, and Mars, have atmospheres substantial enough to generate weather. All have impact craters and tectonic surface features such as rift valleys and volcanoes. The term inner planet should not be confused with interior planet, which designates those planets that are closer to the sun than Earth. For example, Mercury and Venus. Speaking of Mercury, Mercury is the closest planet to the sun, and on average, all seven other planets. The smallest planet in the solar system. Mercury has no natural satellites. Besides impact craters, its only known geographical features are lobed ridges or rupies, the Latin word for cliffs, that were probably produced by a period of contraction early in its history. Mercury's very tenuous atmosphere consists of atoms blasted off its surface by the solar wind. Its relatively large iron core and thin mantle have not yet been adequately explained. Hypotheses include that its outer layers were stripped off by a giant impact, or that it was prevented from fully accreting by the young sun's energy. Venus. Venus is zero point 0.7 AU from the sun, is close in size to Earth, and, like Earth, has a thick silicate mantle around an iron core, a substantial atmosphere, and evidence of internal geological activity. It is much drier than Earth, and its atmosphere is 90 times as dense. Venus has no natural satellites. It is the hottest planet, with surface temperatures over 400 degrees Celsius or 752 degrees Fahrenheit, most likely due to the amount of greenhouse gases in the atmosphere. No definitive evidence of current geological activity has been detected on Venus, but it has no magnetic field that would prevent depletion of its substantial atmosphere, which suggests that its atmosphere is being replenished by volcanic eruptions. Earth. Earth, 1 AU from the sun, is the largest and densest of the inner planets, the only one known to have current geological activity, and the only place where life is known to exist. Its liquid hydrosphere is unique among the terrestrial planets, and it is the only planet where plate tectonics has been observed. Earth's atmosphere is radically different from those of the other planets, having been altered by the presence of life to contain 21% free oxygen. It has one natural satellite, the Moon, the only large satellite of a terrestrial planet in the solar system. Mars, 1.5 AU from the Sun, is smaller than Earth and Venus. It has an atmosphere of mostly carbon dioxide, with a surface pressure of 6.1 millibars, roughly 0.6% that of Earth. Its surface, peppered with vast volcanoes such as Olympus Mons and rift valleys such as Valles Marineris, shows geological activity that may have persisted until as recently as 2 million years ago. Its red color comes from iron oxide, rust, in its soil. Mars has two tiny natural satellites, Deimos and Phobos, thought to be either captured asteroids or ejected debris from a massive impact early in Mars history. The asteroid belt. Asteroids, except for the largest series, are classified as small solar system bodies and are composed mainly of refractory, rocky, and metallic minerals, with some ice. They range from a few meters to hundreds of kilometers in size. Asteroids smaller than 1 meter are usually called meteoroids, and micrometeoroids, grain sized, depending on different, somewhat arbitrary definitions. The asteroid belt occupies the orbit between Mars and Jupiter, between 2.3 and 3.3 AU from the Sun. It is thought to be remnants from the solar system's formation that failed to coalesce because of the gravitational interference of Jupiter. The asteroid belt contains tens of thousands, possibly millions of objects over 1 kilometer in diameter. Despite this, the total mass of the asteroid belt is unlikely to be more than 1,000th of that of Earth. The asteroid belt is very sparsely populated. Spacecraft routinely pass through without incident. Ceres 2.7 AU is the largest asteroid, a protoplanet and dwarf planet. It has a diameter of slightly under 1,000 kilometers and a mass large enough for its own gravity to pull it into a spherical shape. Ceres was considered a planet when it was discovered in 1801 and was reclassified to asteroid in the 1850s as further observations revealed additional asteroids. It was classified as a dwarf planet in 2006 when the definition of planet was created. Asteroid groups. Asteroids in the asteroid belt are divided into asteroid groups and families based on their orbital characteristics. Asteroid moons are asteroids that orbit larger asteroids. They are not as clearly distinguished as planetary moons, sometimes being almost as large as their partners. The asteroid belt also contains main belt comets, which may have been the source of Earth's water. Jupiter Trojans are located in either of Jupiter's L4 or L5 points, gravitational stable regions leading and trailing a planet in its orbit. The term Trojan is also used for small bodies in any other planetary or satellite Lagrange point. Hilda asteroids are in a 2.3 resonance with Jupiter. That is, they go around the Sun 3 times for every 2 Jupiter orbits. The inner solar system also contains near-Earth asteroids, many of which cross the orbits of the inner planets. Some of them are potentially hazardous objects. Stick around, we're going through the outer solar system. The outer region of the solar system is home to the giant planets and their moons. The Centaurs and many short period comets also orbit in this region. Due to their greater distance from the Sun, the solid objects in the outer solar system contain a higher proportion of volatiles, such as water, ammonia, and methane, than those of the inner solar system, because the lower temperatures allow these components to remain solid. Outer planets. The 4 outer planets, or giant planets, sometimes called Jovian planets, collectively make up 99% of the mass known to orbit the Sun. Jupiter and Saturn are together more than 400 times the mass of Earth and consist overwhelmingly of hydrogen and helium. Uranus and Neptune are far less massive, less than 20 Earth masses each, and are composed primarily of ices. For these reasons, some astronomers suggest they belong in their own category, ice giants. All 4 giant planets have rings, although only Saturn's rings system is easily observed from Earth. The term superior planet designates planets outside Earth's orbit, and thus both include the outer planets and Mars. Jupiter. Jupiter is 5.2 AU. It's 2.5 times the mass of all the other planets put together. It is composed largely of hydrogen and helium. Jupiter's strong internal heat creates semi-permanent features in its atmosphere, such as cloud bands and the Great Red Spot. Jupiter has 79 known satellites. The 4 largest, Ganymede, Callisto, Io, and Europa, show similarities to the terrestrial planets, such as volcanism and internal heating. Ganymede, the largest satellite in the solar system, is larger than Mercury. Saturn, 9.5 AU, distinguished by its extensive ring system, has several similarities to Jupiter, such as its atmospheric composition and magnetosphere. Although Saturn has 60% of Jupiter's volume, it is less than a third as massive. Saturn is the only planet of the solar system that is less dense than water. The rings of Saturn are made up of small ice and rock particles. Saturn has 82 confirmed satellites, composed largely of ice. Two of these, Titan and Enceladus, show signs of geological activity. Titan, the second largest moon in the solar system, is larger than Mercury and the only satellite in the solar system with a substantial atmosphere. Uranus, 19.2 AU, is the lightest of the outer planets. Uniquely among the planets, it orbits the sun on its side. Its axial tilt is over 90 degrees to the ecliptic. It has a much colder core than the other giant planets and radiates very little heat into space. Uranus has 27 known satellites, the largest ones being Titania, Oberon, Umbriel, Ariel, and Miranda. Neptune, 30.1 AU. Though slightly smaller than Uranus, is a more massive and hence more dense. It radiates more internal heat, but not as much as Jupiter or Saturn. Neptune has 14 known satellites. The largest, Triton, is geologically active with geysers of liquid nitrogen. Triton is the only large satellite with a retrograde orbit. Neptune is accompanied in its orbit by several minor planets, termed Neptune Trojans, that are in 1-to-1 resonance with it. Centaurs. The centaurs are icy comet-like bodies whose orbits have semi-major axes greater than Jupiter's, 5.1 AU, and less than Neptune's, 30 AU. The largest known centaur, 10199 Chariklo, has a diameter of about 250 kilometers. The first centaur discovered, 2060 Chiron, has also been classified as Comet 95P because it develops a coma just as comets do when they approach the sun. Comets. Comets are small solar system bodies, typically only a few kilometers across, composed largely of volatile ices. They have highly eccentric orbits, generally a perihelion within the orbits of the inner planets, and an apollyon far beyond Pluto. When a comet enters the inner solar system, its proximity to the sun causes icy surface to sublimate and ionize, creating a coma, a long tail of gas and dust, often visible to the naked eye. Short period comets have orbits lasting less than 200 years. Long period comets have orbits lasting thousands of years. Short period comets are thought to originate in the Kuiper Belt, whereas long period comets, such as Hale-Bopp, are thought to originate in the Oort cloud. Many comet groups, such as the Kreutz Sungrazers, formed from the breakup of a single parent. Some comets with hyperbolic orbits may originate outside the solar system, but determining their precise orbits is difficult. Old comets that have had most of their volatiles driven out by solar warming are often categorized as asteroids. Let's keep on going. Through the trans-Neptunian region. Beyond the orbit of Neptune lies the area of the trans-Neptunian region, with the donut-shaped Kuiper Belt, home of Pluto and several other dwarf planets, and an overlapping disk of scattered objects, which is tilted toward the plane of the solar system and reaches much further out than the Kuiper Belt. The entire region is still largely unexplored. It appears to consist overwhelmingly of many thousands of small worlds, the largest having a diameter only a fifth that of Earth and a mass far smaller than that of the Moon, composed mainly of rock and ice. This region is sometimes described as the third zone of the solar system, enclosing the inner and the outer solar system. The Kuiper Belt. The Kuiper Belt is a great ring of debris, similar to the asteroid belt, but consisting mainly of objects composed primarily of ice. It extends between 30 and 50 AU from the Sun, though it is estimated to contain anything from dozens to thousands of dwarf planets. It is comprised mainly of small solar system bodies. Many of the large Kuiper Belt objects, such as Quaoar, Varuna, and Orcus, may prove to be dwarf planets with further data. There are estimated to be over 100,000 Kuiper Belt objects with a diameter greater than 50 kilometers, but the total mass of the Kuiper Belt is thought to be only a tenth or even a hundredth the mass of Earth. Many Kuiper Belt objects have multiple satellites, and most have orbits that take them outside the plane of the ecliptic. The Kuiper Belt can be roughly divided into the classical belt and the resonances. Resonances are orbits linked to that of Neptune, for example, twice or every 3 Neptune orbits or once every 2. The first resonance begins within the orbit of Neptune itself. The classical belt consists of objects having no resonance with Neptune and extends from roughly 39.4 AU to 47.7 AU. Members of the classical hyperbelt are classified as cubewanos after the first of their kind to be discovered, 15760 Albion, which previously had the provisional designation 1992 QB, and are still near primordial low eccentricity orbits. Pluto and Charon. The dwarf planet Pluto, 39 AU average, is the largest known object in the Kuiper Belt. When discovered in 1930, it was considered to be the 9th planet. This changed in 2006 with the adoption of a formal definition of planet. Pluto has relatively eccentric orbit inclined 17 degrees to the ecliptic plane and ranging from 29.7 AU from the Sun at perihelion within the orbit of Neptune to 49.5 AU at aphelion. Pluto has 3-2 resonance with Neptune, meaning that Pluto orbits twice around the Sun for every 3 Neptunian orbits. Kuiper Belt objects whose orbits share this resonance are called Plutinos. Charon, the largest of Pluto's moons, is sometimes described as part of a binary system with Pluto, as the two bodies orbit a barycenter of gravity above their surfaces. They appear to orbit each other. Beyond Charon, 4 much smaller moons, Styx, Nix, Kerberos, and Hydra, orbit within the system. Makemake and Haumea. Makemake, 45.79 AU average, although smaller than Pluto, is the largest known object in the classical Kuiper Belt. That is, a Kuiper Belt object not in confirmed resonance with Neptune. Makemake is the brightest object in the Kuiper Belt after Pluto. It was assigned a naming committee under the expectation that it would prove to be a dwarf planet in 2008. Its orbit is far more inclined than Pluto's at 29 degrees. Haumea, 43.13 AU average, is in an orbit similar to Makemake, except that it is in a temporary 712 orbital resonance with Neptune. It was named under the same expectation that it would prove to be a dwarf planet, though subsequent observations have indicated that it may not be a dwarf planet after all. Scattered disk. The scattered disk, which overlaps the Kuiper belt but extends out to about 200 AU, is thought to be the source of short period comets. Scattered disk objects are thought to have been ejected into erratic orbits by the gravitational influence of Neptune's early outward migration. Most scattered disk objects, or SDOs, have perihelia within the Kuiper belt, but apihelia far beyond it, some more than 150 AU from the Sun. SDOs' orbits are also highly inclined to the ecliptic plane and are often almost perpendicular to it. Some astronomers considered the scattered disk to be merely another region of the Kuiper belt and describe scattered disk objects as scattered Kuiper belt objects. Some astronomers also classify centaurs as inward scattered Kuiper belt objects, along with the outward scattered residents of the scattered disk. Eris, 68 AU average, is the largest known scattered disk object and caused a debate about what constitutes a planet because it's 25% more massive than Pluto and about the same diameter. It is the most massive of the known dwarf planets. It has one known moon, Dicynomia. Like Pluto, its orbit is highly eccentric, with a perihelion of 38.2 AU, roughly Pluto's distance from the Sun, and an aphelion of 97.6 AU, and steeply inclined to the elliptic plane. 2007 OR, 67.4 AU average, is the second largest scattered disk object and the largest object in the solar system without an official name. It is the fifth largest and fifth most massive trans-Neptunian object after Pluto, Eris, Haumea, and Makemake. Similarly to Eris, its orbit is highly eccentric and steeply inclined to the ecliptic plane. It is quite possibly a dwarf planet. Let's keep going out to the farthest regions. The point at which the solar system ends and interstellar space begins is not precisely defined because its outer boundaries are shaped by two separate forces, the solar wind and the sun's gravity. The limit of the solar wind's influence is roughly 4 times Pluto's distance from the sun. This heliopause, the outer boundary of the heliosphere, is considered the beginning of the interstellar medium. The sun's heliosphere, the effective range of its gravitational dominance, is thought to extend up to 1,000 times farther and encompasses the theorized Oort cloud. Heliosphere. The heliosphere is a stellar wind bubble, a region of space dominated by the sun, which radiates at roughly 400 kilometers its solar wind, a stream of charged particles, until it collides with the wind of the interstellar medium. The collision occurs at the termination shock, which is roughly 80 to 100 AU from the sun, upwind of the interstellar medium, and roughly 200 AU from the sun downwind. Here, the wind slows dramatically, condenses, and becomes more turbulent, forming a great oval structure known as the heliosheath. This structure is thought to look and behave very much like a comet's tail, extending outward for a further 40 AU on the upwind side, but tailing many times that distance downwind. Evidence from Cassini and Interstellar Boundary Explorer spacecraft has suggested that it is forced into a bubble shape by the constraining action of the interstellar magnetic field. The outer boundary of the heliosphere, the heliopause, is the point at which the solar wind finally terminates and is the beginning of interstellar space. Voyager 1 and Voyager 2 are reported to have passed the termination shock and entered the heliosheath at 94 and 84 AU from the Sun, respectively. Voyager 1 is reported to have crossed the heliopause in August 2012. The shape and form of the outer edge of the heliosphere is likely affected by the fluid dynamics of interactions with the interstellar medium, as well as solar magnetic fields prevailing to the south. For example, it is bluntly shaped with the northern hemisphere extending 9 AU farther than the southern hemisphere. Beyond the heliopause, at around 230 AU, lies the bow shock, a plasma wake left by the sun as it travels through the Milky Way. Due to the lack of data, conditions in local interstellar space are not known for certain. It is expected that NASA's Voyager spacecraft, as they pass the heliopause, will transmit valuable data on radiation levels and solar wind to Earth. How well the heliosphere shields the solar system from cosmic rays is poorly understood. A NASA-funded team has developed a concept of vision mission dedicated to sending a probe to the heliosphere. Detached objects. 90377 Sedna 520 AU average is a large reddish object with a gigantic, highly elliptical orbit that takes it from about 76 AU at perihelion to 940 AU at aphelion, and takes 11,400 years to complete. Mike Brown, who discovered the object in 2003, asserts that it cannot be part of the scattered disk or the Kuiper belt because its perihelion is too distant to have been affected by Neptune's migration. He and other astronomers consider it to be the first in an entirely new population, sometimes termed distant detached objects or DDOs, which also may include the object 2000 CR, which has a perihelion of 45 AU and aphelion of 415 AU and an orbital period of 3,420 years. Brown terms this population of the inner Oort cloud because it may have formed through a similar process, although it is far closer to the Sun. Sedna is very likely a dwarf planet, though its shape has yet to be determined. The second unequivocally detached object with a perihelion farther than Sedna's at roughly 81 AU is 2012 VP, discovered in 2012. Its aphelion is only half of that of Sedna's, 400 to 500 AU. Whew! Let's go through the Oort cloud. We've mentioned it many times. The Oort cloud is a hypothetical spherical cloud of up to 1 trillion icy objects that is thought to be the source for all long period comets and to surround the solar system at roughly 50,000 AU, around 1 light year, and possibly as far as 100,000 AU. It is thought to be composed of comets that were ejected from the inner solar system by gravitational interactions with outer planets. Oort cloud objects move very slowly and can be perturbed by infrequent events such as collisions, the gravitational effects of a passing star, or the galactic tide, the tidal force exerted by the Milky Way. Boundaries. Much of the solar system is still unknown. The sun's gravitational field is estimated to dominate the gravitational forces of surrounding stars out to about 2 light years, 125,000 AU. Lower estimates for the radius of the Oort cloud, by contrast, do not place it farther than 50,000 AU, despite discoveries such as Sedna, the region between the Kuiper Belt and the Oort cloud, and areas tens of thousands of AU in radius, is still virtually unmapped. There are also ongoing studies of the region between Mercury and the Sun. Objects may yet be discovered in the solar system's uncharted regions. Currently, the furthest known objects, such as Comet West, have apelia of around 70,000 AU from the Sun. But as the Oort cloud becomes better known, this may change. That's pretty much it for the solar system, but let's give you some context in the galaxy. The solar system is located in the Milky Way, a barred spiral galaxy with a diameter of about 100,000 light years, containing more than 100 billion stars. The Sun resides in one of the Milky Way's outer spiral arms, known as the Orion Cygnus Arm, or local spur. The Sun lies between 25,000 and 28,000 light years from the galactic center, and its speed within the Milky Way is about 220 kilometers per second, so that it completes one revolutionary every 225 to 250 million years. This revolution is known as the solar system's galactic year. The solar apex, in the direction of the Sun's path through interstellar space, is near constellation Hercules in the direction of the current location of the bright star Vega. The plane of the ecliptic lies at an angle of about 60 degrees to the galactic plane. The solar system's location in the Milky Way is a factor in the evolutionary history of life on Earth. Its orbit is close to circular, and orbits near the Sun are at roughly the same speed as that of the spiral arm. Therefore, the Sun passes through arms only rarely, because spiral arms are home to a far larger concentration of supernovae, gravitational instabilities, and radiation that could disrupt the solar system. This has given Earth long periods of stability for life to evolve. The solar system also lies well outside the star crowded environs of the galactic center. Near the center, gravitational tugs from nearby stars could perturb bodies in the Oort cloud and send many comets into the inner solar system, producing collisions with potentially catastrophic implications for life on Earth. The intense radiation of the galactic center could also interfere with the development of complex life. Even at the solar system's current location, some scientists have speculated that recent supernovae may have adversely affected life in the last 35,000 years by flinging pieces of expelled stellar core towards the Sun as radioactive dust grains and larger comet-like bodies. The neighborhood. The solar system is in the local interstellar cloud, or local fluff. It is thought to be near the neighboring G cloud, but it is not known if the solar system is embedded in the local interstellar cloud, or if it is in the region where the local interstellar cloud and G cloud are interacting. The local interstellar cloud is an area of denser cloud in an otherwise sparse region known as the local bubble, an hourglass-shaped cavity in the interstellar medium, roughly 300 light years across. The bubble is suffused with high-temperature plasma that suggests it is the product of several recent supernovae. There are relatively few stars within 10 light years of the Sun. The closest is the triple star system Alpha Centauri, which is about 4.4 light years away. Alpha Centauri A and B are a closely tied pair of Sun-like stars, whereas the small red dwarf Proxima Centauri orbits the pair with a distance of 0.2 light year. In 2016, a potentially habitable exoplanet was confirmed to be orbiting Proxima Centauri. Called Proxima Centauri b, the closest confirmed exoplanet to the Sun. The stars next closest to the Sun are the red dwarf's Barnard star, Wolf 359, and Leyland 21185. The largest nearby star is Sirius, a bright main sequence star roughly 8.6 light years away and roughly twice the Sun's mass, and that is orbited by a white dwarf, Sirius B. The nearest brown dwarfs are the binary Lumen 16 system at 6.6 light years. Other systems within 10 light years are the binary red dwarf system, Luton 726-8, and the solitary red dwarf Ross 154. The closest solitary sun-like star to the solar system is Tau Ceti at 11.9 light years. It has roughly 80% of the sun's mass, but only 60% of its luminosity. The closest known free-floating planetary mass object to the sun is WISE 0855-0714, an object with a mass less than 10 Jupiter masses, roughly 7 light years away. Let's finish off this discussion of the solar system with a comparison with extrasolar systems. Compared to many other planetary systems, the solar system stands out in lacking planets interior to the orbit of Mercury. The known solar system also lacks super-Earths. Planet 9 could be a super-Earth beyond the known solar system. Uncommonly, it has only small rocky planets and large gas giants. Elsewhere, planets of intermediate size are typical, both rocky and gas. There is no gap as seen between the size of Earth and of Neptune, with a radius 3.8 times as large. Also, these super-Earths have closer orbits than Mercury. This led to the hypothesis that all planetary systems start with many close-in planets, and that typically a sequence of their collisions causes consolidation of mass into few larger planets, but in case of the solar system, the collisions cause their destruction and ejection. The orbits of solar system planets are nearly circular. Compared to other systems, they have smaller orbital eccentricity, although there are attempts to explain it partly with a bias in the radial velocity detection method and partly with long interactions of quite high number of planets. The exact causes remain undetermined. That's about all I have for the solar system and the surrounding areas. If you want to learn more, I encourage you to check out a library. Yes, a library. I hope you learned a little bit more about solar systems. I sure did. Thank you so much for sticking with me on the What Makes You Smarter podcast. Once again, if you'd like to tell your story, I encourage you to check out my other podcast, What Makes You Famous. Find it everywhere using the hashtag What Makes You Famous. That's it for this edition of What Makes You Smarter. It's Keys Dan, RadioWhat.com, DJLittleRock.com. Peace. I'm out of here. If you like what you hear, I encourage you to follow What Makes You Smarter podcast everywhere on social media. Find it on Facebook at What Makes You Smarter. Find it on Instagram at What Makes You Smarter. And find it on Twitter at Smarter What? And find it on YouTube. A username, Keys Dan. Leave What Makes You Smarter podcast a review and subscribe. Listen to What Makes You Smarter podcast on Spotify, iTunes, YouTube, Stitcher, Google Podcasts, Podcast Addict, my personal favorite, and anywhere you find podcasts. Learn with me on my podcast, What Makes You Smarter. Support What Makes You Smarter podcast using my PayPal, paypal.me/KeysDan. Support this podcast Email info@radiowhat.com if you want to hear a certain topic in your ears right here on the program. What Makes You Smarter is a production of Keys Dan Enterprises Incorporated at keysdan.com. Thank you for listening.